This is a recording for the March 5th meetup, Building LLMs, potentially sponsored by Manning Publications, and a to-be-named cloud GPU vendor providing GPU time for participating members. And so the quid pro quo to the corporate sponsors is that they get publicity and potentially some material they may be able to use at the level of a solution architect. The reason that this is maybe valuable to them today is because of the rapid interest and growth in LLMs. The gap in content has been exacerbated by the sudden appearance of DeepSeek. And so the other caveat for members is that it's almost impossible to develop the skills that LLM companies are looking for. So those skills predominantly relate to distributed training and inference serving using a GPU cluster. Those are very different skills than just building a chat GPT model on a MacBook. And so that being said, once you do build a chat GPT model on a MacBook or a Jupyter notebook, that's a first step. And a second step, which is going through Karpathy's LLM.c, that does build skills that involve distributed training and inference serving. And so we can get there, but it will require corporate support. And so that being said, let's cover what we did last week first as a quick follow-up. So we briefly pointed to a video from Sebastian Raschka from a couple years ago when he was doing a deep learning class, which covers the topic of backpropagation through time. Backpropagation is a fundamental deep learning algorithm which calculates gradients based on the chain rule, the calculus chain rule. So you start with a function. It can be the loss function. And that loss function, which I think in the video is a squared exponential, you take the partial derivative of that with respect to all the weights, and that calculates the gradient updates. As you feed in each input batch, you update the weights, and the idea is that after a large number of inputs, you've converged to a set of weights that you can use that defines your model. And so you'll multiply input values into that model, you get output. So the idea is, so backpropagation through time, the ability to do these partial derivatives is important. Karpathy mentioned this in his LLM.c talk to Excel Ventures, where the video link is here. He used the equation for layer norm, did the partial derivatives with respect to the weights, and then he verified that equation using PyTorch. And so in verifying that equation, once he had the derivatives, he was able to use that and implement that in C. So the issue is that there are sometimes errors in this. The company Unsloth found an error in gradient accumulation. Unsloth also has, as part of their hiring process, a 5-part interview question, which they've made public. And the last question says, calculate backprop for Apple's cross-cut entropy loss, and then find a memory-efficient implementation of that. And so backprop is considered a fundamental skill for deep learning, and we can get back to that. But right now, we're going to table any more work on backprop in favor of building more GPT models on Google Colab, getting people to implement attention mechanisms. And then we're going to cover reinforcement learning and fine-tuning before we get to backprop. For this section of the video, we're going to cover inferencing. So at the end of this video, we're going to cover a lab where we build a GPT model for our character RNN equivalent. And we're going to try, over the next week, implementation of different types of flash mechanisms for training. And so what we don't cover, which we need to discuss a little bit before we get there, is what are the impacts of attention on inference serving? So with the recent explosion of DeepSeek, there's been some speculation as to the amount of money that they're making, which drives everything. And so it's estimated that they may make a 500% profit margin and that they have 23% of ChatGPT users. If that is or is not exactly true, I don't know. But it is true that they've open sourced and made public what their innovations are, and those are going to impact our implementation of Flash, and it's also impacting real time the investments in inference. Specifically, there's been a bigger investment in inference over the last 6 months than in the past couple of years because of the revenue associated with open LLM or LLM models in general. And so, excuse me. Sorry, I don't know how to pause this video. And I can't restart making these videos every time I cough. So figure 1.8 of chapter 1 is a block diagram of what an output stage of an LLM looks like. Specifically, this is known as an autoregressive tokenization pattern. What does that mean? So that means that the input of one stage of a decoder produces an output, and that output is fed into the input stage of another decoder. So in this block diagram, an LLM output consists of a series of decoder in series. And so we have to distinguish two concepts, autoregressive versus agentic. And these are often confused, and it's important to distinguish the difference because we're going to discuss KV caches next. And that has a big impact on cost, the KV cache, once you look at the amount of memory it takes. And autoregressive flow, again, means that the output token becomes the input of the next stage, and the output of that stage becomes the input of the next stage. There's a cascade or serial effect. An agentic workflow refers to a user typing in a question which consists of multiple tokens, getting an answer which consists of lots of text, and then a follow-up question. So the question and follow-up question may have related tokens, and the answers may have related tokens. So those are indicated in the respective colors. Like yellow means that there's some similarity in the tokens used, and green means that there's some similarity in the output tokens used. These two patterns relate to different types of data structures used in an inference server. So let's look at the calculation of attention. And this calculation of attention on the output stage is similar to the calculation of attention on the input stage. On the input stage, when we're training, an input vector or an embedding is multiplied 3 times. First to a query vector, second to a key matrix, a third to a value matrix. These values of these weight matrices are calculated on training. You put the whole training set through your LLM, you train that, and at the end of your training set, you've got a set of weights that are converged to what you think the model should be, what represents your input corpus. Now, how does that multiplication look in detail? So as you're serving the output request, the auto tokenizer or the output requests, what does the multiplication look like in the matrix? So as you progress from word to word to word, you're incrementing the columns for the key matrix and the rows for the value matrix. And so what that means is that as you progress from word to word to word, you can use the value, the row, and the column values of the previous word, and you can cache that. And so you only have to compute the last one. And so this is distinguished from and different than other types of encoder decoders. The KV cache is only for autoregressive decoders. Not all decoders are autoregressive. For example, a BERT decoder is not autoregressive, and it cannot use a KV cache. This is only for a very specific type of implementation. So let's look at the memory usage of a typical chat GPT model, which is autoregressive and which has 30 billion parameters. The 30 billion parameters is considered small by today's standards. A 30 billion parameter KV cache would be 180 gigs, whereas the model itself would be 60 gigs. So the KV cache would be 3 times bigger than the model. And so what does this mean? How do you implement this? So to borrow some theory from an operating system, which maps virtual memory, as called logical memory in this diagram, to physical memory, you require a page table. It's like a little lookup table. And that size is one of your parameters, and also the size of the page is a parameter. And so this this allows you to have a much bigger memory space than is physically available by swapping in and out how much physical memory you have at the expense of this swapping information and the maintenance of this page table data structure. So this is similar to how this product called VLLM or Virtual LLM works. It implements something called a page detention cache, which maps physical GPU memory to virtual GPU memory. And this has been a recent development, maybe in the last year or so. It was created by 2 undergraduate Berkeley students. And since then, it's migrated into almost all the inference products, including PyServe or PyTorch. And so VLLM is now a PyTorch sponsored project, meaning that it's been integrated inside the source code of PyTorch. It's a functional part of PyTorch. They have a nightly CI flow, which evaluates the performance of VLLM, and there are some metrics on VLLM. Why do I mention this, and why is this important? So this is important from a job perspective because I get a lot of requests, almost monthly, asking for VLLM engineers. And the simplest the simplest base level is just to be familiar with the code and to be able to do the bug fixes involved in these nightlies. All these nightly commits in the CI process have bug fixes. They can be different versions. They can be stupid things like constants off. It doesn't matter. But this is the quickest way to get a job, to get familiarity with this to the VLLM framework or software. And so congruent to that, well, okay, let's stop here. And so we're going to do a lab after this, and we're going to get everybody on building a GPT, mini GPT for a character RNN, where you feed in a bunch of text and you generate the next character for the next word. And so that's going to get everybody aligned on doing lab work, and that's going to get us hopefully more toward the progress of making demos. So one thing before we get to the lab is that we're going to talk about tokenization a little bit. This comes from Karpathy's talk on LLM.c. The book doesn't really mention tokenization. Tokenizers have a visible impact on the performance of an LLM. What does that mean? So Karpathy pointed this out. It's if I'm designing an LLM to generate Python code, I'm going to feed in Python code. And there's a website that shows you the effect of tokenization, meaning that a first generation tokenizer, which is what GPT uses, it looks at the spacing for a Python indent or spacing, and it tokenizes each space or tab into a separate space. So this is the first version. So the second version for GPT-4, they created one token for all the spaces, right? So what does this mean? That means that there's less wasted space for all these tokens. Like, you don't have to store these because these don't have any meaning in Python code. Whereas you're storing one token here, and that means a new line, right? So that means that the LLM can parse this better than this. It takes less effort. And so there are other issues with parsing English versus Python text. For instance, an underscore is considered punctuation. And in English, it's common to make those two separate words. Whereas in Python, this should be considered as one identifier. Now, we don't have that yet. We still have 2 different identifiers. And here we have 3 different identifiers. And so maybe it's easier for the LLM to parse this as code versus this because there's less storage space. It's unknown if, again, this requires experience. You would have to build this and figure out how to quantify this. I'm sure there are micro benchmarks for this, but in the larger benchmarks, we don't have that available to the public. Okay, so we're going to do a lab, and we're going to build a character RNN. I'm going to terminate the presentation, and there are some other issues with agentic workflows that we're not going to cover in this video, but we will cover it in the Meetup group. And there's not enough development here. Like, clearly, this is another data structure built on top of VLLMs, but until we implement the attention mechanisms, this won't make much sense. Like, we can look at this slide, and that's all we can look at. We won't understand the implementation details until we understand attention and VLLMs in more detail. Okay, so we're going to terminate the video, and then we'll wait for next week.